When a solute dissolves in a solvent, it is an equilibrium process that is similar to the evaporation process. So initially you have your solute dissolving, and the rate of dissolving is going to be much higher than the rate of recrystallization, because when you first start, there's nothing in the solution to recrystallize. But as more and more solute dissolves, the concentration of dissolved solute increases and the rate of recrystallization increases. And at some point, you'll get a dynamic equilibrium where those rates are equal. So we have sodium chloride solid dissolving into sodium ions and sodium ions combining, recrystallizing to form the solid again. So here we have a beaker of water and a chunk of sodium chloride in there. Initially, all that's going to happen is that we're dissolving. There aren't any sodium and chloride ions here to recrystallize, so that can't happen. As it dissolves, we get more and more sodium chloride ions present in the solution. The rate of recrystallization depends on the concentration of those ions in solution. So as the dissolving keeps occurring, then the rate of recrystallization is going to increase. And so eventually we get to this point where dissolving and recrystallizing are happening at equal rates. Just like when we talked about a beaker or a flask that's closed and the water evaporates and then the gas molecules get trapped. We have condensation and evaporation happening at the same time. Any questions? We refer to a solution where the dissolved solute is in dynamic equilibrium with the solid solute as being a saturated solution. If you add more solute to that, it will not dissolve. You can think of the solvent as being full, like the ground being saturated with water. The solvent is full, it can't take any more. An unsaturated solution has less than that equilibrium amount, and so if you add more solute, it will dissolve. Yeah?
Going back to the last slide.
Mm-hmm.
Just since the recrystallization rate and this solution rate are the same,
Yeah.
does that mean the chunk of NaCl is always going to be there? Or would it all dissolve away?
Okay, so that's an excellent question. So these rates are the same. Does that mean this chunk of sodium chloride is always going to be there, or is it going to go away? In a saturated solution, there will always be some solid present. And if you were to monitor and measure the amount of solid over time, the mass of it would be the same. It may change shape though, because as the ions dissolve and recrystallize, they may recrystallize in a different place than they originally came from. And typically what happens in a saturated solution, as dissolving and recrystallizing occur, the crystals that are present grow larger and more perfect. So you could start with little grains of salt, and if you wait long enough, you might end up with one perfect crystal of sodium chloride. Because as they come in, they are going to arrange themselves perfectly. They're in no hurry. We're not forcing them to precipitate quickly. So they'll recrystallize leisurely, and they will exclude impurities, because impurities would increase the potential energy of the crystal. And so they're going to come in a way that excludes the impurities. Yeah?
I was going to ask, so in a saturated, so like you had some saturated mixture of NaCl and like put more in there, it wouldn't dissolve, right?
Correct.
So does that mean that like certain substances have like a maximum molarity?
Yes.
So
Yep.
if something is saturated, it's at its maximum molarity?
Yep. There's a maximum concentration, molarity, for sodium chloride in water. It's going to depend somewhat on temperature, but you can't just have an infinite. You can't just mix them in any proportions. Yeah, and we'll get to that. It's called solubility. So there was saturated and unsaturated, and then there's supersaturated. A supersaturated solution contains more than the equilibrium amount. So I just said there's a maximum. How's that going to work? Well, I'll come back to this. The solubility of most solids in water increases with increasing temperature. So here's sodium chloride. At 0 degrees Celsius, the solubility looks like to be about 34 grams of sodium chloride in 100 grams of water. And as you heat the water, the solubility for sodium chloride increases, not very much, but it does, and over here it looks like it might be 40 grams. Some substances, though, have a large temperature dependence. So here for potassium nitrate, down here it's like, 12, 13 maybe. And at, 55 degrees, it's 100 grams per 100 grams. So you can dissolve an equal amount of potassium nitrate in water, and it will dissolve. The way you form a supersaturated solution is you heat it up. You heat it up at a higher temperature, this will dissolve. So if I have 90 grams of potassium nitrate dissolved in 100 grams of water, and I let this cool down, it may begin to crystallize right away. Some things definitely do that. Other things, like what I've got here in the flask, sodium acetate, are known for not doing that. And so as you cool it down, it still remains in solution. Now that is not a stable situation. It's a bit like the supercooled liquid in experiment, is that 11B? No, it was 11A, where you took the sodium thiosulfate pentahydrate crystals and you melted them just by heating them in a test tube. And then you cooled the test tube in ice water until it got down to about 30 degrees Celsius. And then you took the ice water away and you dropped a crystal in there, and it began to freeze right away, right? It requires a nucleation site for those crystals to begin forming. If there's no nucleation site present, it may remain in solution, but it's unstable. I think of it a little bit like Bugs Bunny or Roadrunner. They run off the cliff and they don't notice immediately. They don't fall. They just keep running. And they don't fall until they realize that they're standing on nothing, right? That's a supersaturated solution. All you have to do is poke it, basically. Say, hey, you ran off the cliff, and then bang, it falls. Okay? So that's what I'm working on here. I heated up this solution. You guys who were here at the beginning saw that was like a solid, right? It was a little bit of water, but it looked pretty solid. And I heated it up, and now it's all liquidy. It looks like thick water. And so we're just going to let it cool down without disturbing it. So don't even send any sharp thoughts its way, okay? Because sometimes just looking at it wrong can mess it up. It worked great yesterday, so hopefully it'll work today. But here I've got a couple of videos of this happening. So that's supersaturated sodium acetate, and they stick some sort of a metal rod in there. And that gives the crystals a place to begin forming. And so they come out of solution very quickly. You watch them grow. Isn't that cool? probably could have cut that off a little sooner, but here's one where they made a whole bunch of sodium acetate supersaturated solutions, and they're just kind of playing with them. So stick some toothpicks in there, and they look like cotton balls growing. And the temperature goes up from around 25 to 52. So this is sometimes called hot ice, because it looks like it's freezing, doesn't it? But it's not. It's precipitating. Solid enough that it'll stand there, but it kind of breaks apart, sort of like a mushy popsicle. Sodium acetate. This is, it's crazy. A liquid that you pour that becomes solid as soon as it hits something. And here she lets it crawl up into the beaker, and it solidifies all the liquid in the beaker. I'm only playing with dominoes. Could have a race. Who's gonna get there first? And there she spelled ice. Looks like ice. It's not ice. Any questions? There's still photographs of that. The supersaturated solution, just disturbing it a little bit, and the crystals began to form, and then it will continue to crystallize until it reaches the saturation point at that temperature, until it reaches the solubility at that temperature. So later, when this cools down to room temperature, we'll do it with our flask here. So recrystallization is a technique that can be used to purify a solid. This is rock candy, which is sugar crystals, and you can try this at home, but if you're going to try it, look up some instructions, because you have to get the right amount at the right temperature or it doesn't work very well. But allowing the sugar solution to cool slowly and the crystals to form slowly, they recrystallize and they dissolve, and they recrystallize and they dissolve. And they form these large, beautiful crystals. It rejects impurities, because the impurities mess up the crystal structure. They mess up the crystal lattice. Gases behave differently at different temperatures than solids do. So generally, solutions of gases in water, the solubility will decrease at higher temperatures. So here we have a photograph of cold soda being poured into a glass and warm soda. And the warm soda, these are the same types of soda. The warm soda is fizzing up and making this big head, and it's going to, overflow if you're not careful. Whereas the cold one isn't doing that as much. When you pour the soda, you're causing the carbon dioxide to come out faster, and it does that much more readily in the warm soda, and so that's why it gets this big head on it. You probably have experience if you leave the soda at room temperature, it goes flat much faster than it does if it's kept cold. This has significance for aquatic life forms because oxygen levels are lower in warm rivers and lakes and oceans. And so you can have thermal pollution. Say a factory is generating wastewater that's warm. The wastewater may be very clean, not have any chemicals in it, but the fact that it's warm when it gets dumped into the river raises the temperature of the river in that area, which causes the oxygen levels to go down, it can cause fish and other things to die. It's also why if you have like tropical fish or non-tropical fish, you want the temperature to be right, because the temperature affects their oxygen levels. So it's pretty important. The solubility of a gas increases with the pressure of the gas above the liquid. This is why cans and bottles of soda are pressurized. So here we have a can of soda. Here's the soda. It's got carbon dioxide dissolved in this aqueous solution, and there's some gas up here, and that's CO2 under pressure. You open the can, psst, that sound is the pressure being released. As soon as you open the container, the soda starts going flat. If you do this with a 2-liter bottle, you uncap the cap, unscrew the cap, and watch the soda. Once you let that pressure out, you can see bubbles start to rise. The bubbles didn't do that beforehand because the pressure of CO2 above the liquid increases the solubility, and so the carbon dioxide is soluble. So here we have a container where we have carbon dioxide, and let's just call that water, and it has reached an equilibrium. So carbon dioxide is soluble in water, but it has its limits. So here we've got it leaving the solution and re-entering the solution. It's not really dissolving and recrystallizing, but you get the idea. It's a lot like evaporation and condensation. If we compress this, so we're increasing the pressure of the CO2 here by changing the volume. Now the concentration, the pressure of the CO2 is larger, and so that's going to increase the rate at which the carbon dioxide dissolves into the water. And this rate will continue to be faster until we establish a new equilibrium. At this new equilibrium, the concentration of carbon dioxide in the water is larger than it was at this lower pressure. It has to be the pressure of that particular gas, though. Just increasing the pressure by putting some other gas in there will not increase the solubility of the carbon dioxide. So they used to sell these things on TV. You could put on your 2-liter bottle of soda and pump it up and put pressure on it, and it was supposed to keep your soda from going flat. But all it was doing was putting air into the bottle. So increasing the pressure of air is mostly nitrogen and oxygen. It's like 0.6% CO2. And it's only the increased pressure of CO2 that's going to increase the solubility of CO2. And so those really didn't do any good. Now, if you pressurize it with CO2, that's a different story. And that's sort of the idea behind the soda stream machines and, the soda fountain at 7-Eleven. In the back, they don't have carbonated soda. They have the syrup, and they have, I don't know exactly how they do it, but they've got carbon dioxide. And you mix them together, and it will remain in solution for a while, but the fizziness is the CO2 coming out. I'm very fond of CO2. So, of course, we can quantify the relationship between the pressure and the solubility of a gas. This is called Henry's law. So the solubility of a gas, which is usually given in moles per liter, is equal to a constant times the partial pressure of that gas above the liquid. This is the Henry's law constant. It's going to depend on the temperature, on the gas, and on the solvent. So lots of different values for this. You definitely don't memorize these. You just look them up. So the Henry's law constant for oxygen in water at 25 degrees is 1.3 times 10 to the minus third molarity per atmosphere. So we can do problems like this. Determine the solubility of oxygen in water at 25 degrees Celsius exposed to air at 1 atmosphere. Assume a partial pressure for oxygen of 0.21 atmospheres. So the solubility of O2 is going to equal the Henry's law constant times the partial pressure of O2. So we need the Henry's law constant. Only reason I remember that is I said it just a minute ago. I got that from the table on the previous page. Let's just double check. Yeah, 1.3 times 10 to the minus 3 molar per atmosphere. So we're given two pressures here. This is the air at 1 atmosphere, and this is the partial pressure of oxygen. This is the pressure that's important. So to find the solubility of oxygen, we're going to use the Henry's law constant, 1.3 times 10 to the minus 3, times 0.21 atmospheres. Two 0.73 times 10 to the minus 4 molar. I'd have two sig figs. So that's small. Yes?
What is the unit for molar again?
The capital M means mole per liter. Mm-hmm. Yeah, I'm not sure why this happens. A lot of students see the capital M and they think, oh, that's moles. No. It's moles per liter of solution. Moles has its own abbreviation, MOL. So capital M is moles per liter.